Hello, before we have discussed some characteristic, trending and time series with our model, and then of course we have looked some idea what's happened to our regression if we put the time variable in our model and without the time variable into our model. And now for this subtopic we want to look and discuss using the trend variable in regression analysis. Okay, if we put the trending variable in our model, it's not necessary we violate the what we call it as the CLRM assumption, classic linear regression model. However, we must carefully that to allow for the fact that unobserved or trending factor that affect YT might also can be correlated with explanatory variable. Okay, if we ignore some trending in our model, we afraid that when we regress the data, there is some problem will exist in our regression model. That's problem we call it as the spurious regression problem, which is referred to the relationship between two or more trending variable and growing over time. But usually when we face very trending variable in our model, if we adding a time trend in our model, sometimes we can eliminate this problem. Okay, let me assume that there is a two variable x1 and x2 affected the y, and this relationship between these two independent variable affected the y can be shown by the equation 10.31. Allowing for the trend especially recognize that I think maybe okay. Now let's assume that we face the two independent variable affected the one independent variable. The two independent is referred to the x1 and x2, and we can see this relationship by the equation 10.31. Okay, and then beside the x1 and x2, we also put the time variable t into our model. That means we usually want to capture the trend factor in our regression. If we assume that the y is growing, of course we estimate or we expected that the coefficient of beta 3 must be positive, or if yt is shrinking, we expected that the coefficient of beta 3 can be negative over time. If equation 10.31 satisfy the CLRM assumption, of course the variable t need to include into our model, and if we omit the t, that means our regression will lead the bias estimator. For example 10.7, let's say we look the relationship between the real per capita housing investment and the price as in the equation 10.32, and of course based on the economics analysis, we expected that the beta 1 is positive sign, and this is some information, the content of the variable in our data. And let's say we plot these two data by the years. When we plot these two variables, we can see that there is some trend, or we can say that the variable IMVPC and the variable price share the common trend. Okay, this is the result of the data. when we regress the equation 10.32. The coefficient of L price is positive and is consistent what we have expected before. And the T statistics show that the L price is highly significant to affect the LIMFPC. Even the per capita investment with respect to the price is very large and statistically significant, but we must carefully because these two variables have the upward trend. To see this, let's perform the two auxiliary regression to evaluate the relationship between the log investment on the T and also the log price on the T. Okay, this is the result data for the two auxiliary regression. Based on these two regression, for the equation for the auxiliary regression 1, we can see that the T variable is significantly affect the real per capita housing investment, and for the second auxiliary regression, we can also see that the T is significantly affect the housing price index. This result show that the variable T is significant to affect the LIMVPC or real per capita housing investment, and also the price or the housing price index in the both auxiliary regression. That means the regression tend to contain substantial serial correlation and the coefficient estimate do reveal the upward trend. Okay, let's now we put the time variable into our model as in the equation 10.33. The results show that when we put the time variable T, the result is much different if we not put the time variable in our model. After we put the time variable in our model, we can see that the price elasticity is negative and statistically not significant. This suggests that we cannot conclude LIMVPC is influenced by the price. That means maybe there is the other factor, and this factor is captured in the time trend and of course unobserved, and this factor is affect the LIMVPC. So that means the equation 10.32 show a superior relationship between the LIMVPC and price due to the fact that price is also trading upward over time. Let's use another example. For this new example, we use the fertile tree data, but we include the time trend linear as in the equation 10.34, and the other is the time trend quadratic as in the equation 10.35. And this is shown for the variable content in our data. This slide is result for the data for the model 1 and the model 2, which the model 1 will not include the time factor, the time variable, and the model 2 we include the time variable, where the last one for the model 3 we put the time quadratic, and the last table we conclude for all model 1, model 2 and model 3 in the one table. The result clearly show that if we put the time variable, or if we not put the time variable in our model, the result of the coefficient is much different. We can see that for the model 2, the coefficient of the PE is more than triple if we compare to the model 1. And it also happened for the pill variable, which is significant in model 1 but not significant in the model 2. For the model 2, we can see that if we look the time variable, the sign positive means that the GFR was falling on average over this period. And for the model 3, the variable PE is quite larger and is statistically significant. Now, the variable P has expected negative effect and is marginally significant, and both trend terms are statistically significant for the model 3. That means the quadratic trend is flexible way to account for the unusual trending behavior of the GFR. The idea we put the time trend in our data is actually we want to create the nice interpretation term of the detrending, the original time series. In other words, we want to detrending the data if we assume that test data have the trend. Let's we assume we regress the YT on the X1 and X2 and also the T, and we get the fit equation as in the equation 10.36. After that, let's say we want to extend the result on the parceling out the interpretation of the LS to show that the estimate of the beta 1 and estimate of the beta 2 can be obtained as the follow. For the step 1, regress each of the Y, X1 and X2 on a constant and also on the time trend T, and after we regress, we save the residual. This regression will make the residual from the each regression have the trend removed. For the step 2, let's we run the regression as the equation 10.37, and we can see that the estimate coefficient of the pi 1 and the pi 2 from the equation 10.37 is exactly same as we get from the equation 10.33 for the coefficient beta hat 1 and beta hat 2. That means the estimate of the beta 1 and beta 2 can be interpreted as the coming from the regression without the time trend. But of course, we want to show that we first detrend the dependent variable and all other independent variable. If T is omitted from the equation 10.36, that means there is no detrending, and the YT might seem to be related to one or more of the XJ, simply because each contains a trend, as we saw in example before. If the trend term is statistically significant and the result change is important way when the time trend is added to a regression, then the initial result without a trend should be treated with suspicious. If the T is omitted from the equation 10.36, we assume that there is no detrending, and the YT maybe can be related to one or more of the x. If the trend term is statistically significant and the result is changed in important way when the time trend is added to a regression, then the initial result without the trend should be treated with the suspicion. To prove this statement, let's see we use again the data as SENV and our basic model as an equation A, and we make some auxiliary regression. And the estimate residual to residual as in the equation B. This is the result for the R and LVPC into the L price and also the time variable. And then we regress the RINVPC to the T. After we regress, we carry out the residual. For the equation, another equation, we regress the L price to the T and we carry out the residual. And then we regress the residual for the RNVC to residual for the L price. The results show that the estimate of coefficient beta 1 from equation A, which is beta 1 is negative 0.381, is almost same we get from the regression of the residual from equation B, which is pi 1 equal to negative 0.381. In the time series analysis, usually if we regress and look the R square, it's very common we can get the R square is very high because usually the dependent variable is trending. Based on the formula of adjusted R square, the estimating of the error variance when the YT is trending usually don't get any problem as long as the time trend is included in our regression. However, when the estimated of the YT follow a linear time trend, it shows that the total sum R square divided by degree of freedom is no longer an unbiased or consistent estimator for the variance of the YT. So, there is a simple method is we compute the usual R square in the regression where the dependent variable has already been detrended. For example, let we use again the model equation 10.31 and then we regress the YT on the T, and after we regress we obtain the residual, and this residual is named by the Y hat double dot. Let's say we regress this residual on the x1, x2 and the t as in the equation 10.39. The results show that usually the R square from the equation 10.40 is no greater than and usually is less if we compare to the R square from the equation 10.36. That means when the YT contains a strong linear time trend, the equation 10.40 can be much less than the usual R square. So, R square in the equation 10.40 will be better reflect how well the x1 and the x2 explain the Y because it nets out the effect of the time trend.